All right, I think we're ready. Well, first we're going to go over two problems from one of the practice sets of problems that are out there because they got several questions. One of them got a lot of questions, and the other one got one or two questions. So we're going to go over those. They're not terribly long, and they're kind of generic. They're not necessarily specific to Exam 1 content. So they're good to go over. But what we're doing the rest of the class today is starting content for Exam 2. So if you remember how I put this course together is the first third is axial stresses and strains. You know, the forces are axially aligned with the object. The middle third is flexural forces, so things are now bending and flexing. And then the last third is torsional and all the other little things that kind of go along with statics and mechanics of materials. So we're about to start the flexural part. Before we do that, though, let's look at these two problems. Let me point out that quiz 2 is open. I actually opened it yesterday a little bit, and it's going to stay open until Friday. But you probably want to go ahead and do quiz 2 because the content, stresses, strain, trusses, that kind of stuff, is content for Exam 1, which is tomorrow. So it would be probably wise to go ahead and do quiz 2, even though it stays open until Friday. I think it's another one that you can take it twice, so you could do it once before, tomorrow, and then if you wanted to redo it again later, you could redo it again. All right, here are, well, that's one of them, but that's not the first one I want to do. This one is problem number, actually it's problem 2 and 3 on, I don't know, an exam practice problems from who knows when. From 2015, or 2016. So quite a while ago. And this is the problem that we're looking at. This one isn't really talking about any kind of mechanics other than this one is all about drawing free body diagrams. So what we're going to do here, why don't we copy all of this so that we can write on it. So we're going to copy that, and then let us put it in here. There. All right. So what this one is doing is not asking you to calculate stresses or anything, but it could be a problem that would lead to some kind of axial stress calculation or something like that. But really all it wants to know is in the segment GH. So let's see, there's G down to H. So in this segment of this weird column, what is the stress? What is the force? Not even the stress. What's the force in this segment? And you've got most of it's pretty straightforward. There's some forces pushing down and pulling up, and you also have these pulleys. It does say, I assume, frictionless pulleys. Just like the rest of this course, we're not dealing with friction. That does create new complications. So we're not doing any frictional devices in this course. So it's frictionless. So what that means as far as frictionless pulley means is that there's some sort of rope or cable that goes around the pulley, and all the pulley does is change the direction of this cable. It doesn't change the force in one side or the other of the cable. It doesn't absorb any of that force, if you want to think of it that way. So the force, no matter where you are in that cable, is the same. So, like I said, this is about drawing a free body diagram, and I want to know the force in this green member that I colored. So I need to cut through that, but then I need to isolate one of these bodies and not leave it connected to anything else. So that means I'm going to need to cut, all of this away, draw that free body diagram. I could do the bottom one also. I could do this. The reason I'm not doing this one is that it's connected to the floor, and I don't have given the reactions from the floor. So there would be reactions right here where the floor is holding on to the member GH that I don't know. So I'd have to solve those and then draw that free body diagram. Whereas if I look at the top free body diagram, it's not connected to anything. It has a bunch of forces on it, but I have the values of all those forces in this chart down here. So that's why I'm going to work on this top free body diagram and not the bottom one down here. So why don't we draw this one, and instead of all the F2, F1, let's put numbers in and do something like this. So there's where we cut it, and it's got all these little platforms on it. I'm not being too worried about drawing, exactly the same shapes. I'm not interested in that. I'm interested in the force that's in this thing. I'm interested in this force. This is the force I want, the internal force in section GH. So that's what I want. So I also have these pulleys hanging off of here, don't I? All right. So let's start putting the forces on this body so that we can add them all together and solve for GH. So F1 at the top, 142. I'm going to leave the units off just because it's going to get really cluttery. These are all in kilonewtons, so this is actually 142,000 newtons. F2, there are two shown and they're not connected together, so that means they are two independent forces. So I've got 81 over here and an additional 81 over here. If they were connected, then it doesn't matter how many arrows there are, it's just one 81 kilonewton force. But if they're separate arrows and not connected together, then they are separate forces. F3, I've got 37, two of those. F4, 233, but it's going the opposite direction. F5 going down again, 296s. Not 296, but 96 twice. The cable, so here and here, I had to cut through that cable. So now I see that internal force. So the cable wraps around the pulley, both of these pulleys, and I can actually see what is F3? It's 37 here, 37 here, 37 here, and 37 here. So there's four 37 kilonewton forces all pulling down. I know they're pulling down. The ones that are labeled on the diagram show that they're pulling down, but I also know that these arrows would be going down because cables and chains and ropes, as far as we're concerned, can only have tension, meaning the arrow is pointing away from the cable. And so I drew the little section of the cable, and then I drew the arrow pointing away from that to indicate that it's in tension. I also, by default, the direction I drew FGH is going away from the body, so I just drew it in tension. I don't actually know that one though, because I haven't solved, I haven't added this all up. I just picked one, and I picked tension. Now, all of these forces are in the Y direction. So I take this free body diagram, summation of forces in the Y direction equals 0, and I add them all up. I will assume that Y is positive when it goes up. I'll put X, over here somewhere just to have it, but I don't actually need X. So all the upward facing ones are going to be positive, and all the negative facing ones are going to be negatives. Or all the downward facing ones are going to be negative. So I've got 142. Again, these are all kilonewtons. Minus 81, or minus 2 times 81, whichever way. Maybe we can write it that way since that might be a little simpler. Minus 2 times 37 plus 2 times 233. Ran out of room, so minus 2 times 96 minus 4 times 37 minus FGH. All those have to add to 0. If they don't add to 0, that means this body that I drew is moving up or down. It doesn't necessarily mean it's moving up or down, it's just moving one of those directions. If it adds to 0, it means it's stationary and it's not moving, not translating. So let's see. 142 minus 2 times 81 minus 2 times 37 plus 2 times 233. That's a plus symbol. It's not a very good one, but now it is. Minus 2 times 96 minus 4 times 37 minus FGH. So I'm just going to move FGH to the other side of the equal sign. So whatever I get, whatever number here equals FGH. I get 32. So I get, therefore, FGH, move to the other sign and drop that negative sign, equals 32. These units would be kilonewtons. There is a 32 kilonewton answer, which is nice when you actually calculate one of the answers. So I think it's C. I think this practice test does actually, on the very last page, have the answers written down. Not the solutions, but the answers. And so hopefully it does come out to be C. It came out positive. That means that I drew this arrow the correct way. That means that this piece, GH anyway, not the whole, not the whole thing, but piece GH, that's the internal force I just calculated, is in tension. And that helps us answer the next part, because part 3 says the floor's action on the column can be best described as, is it pushing up on the column, is it pulling down on the column, or is it not reacting? So not reacting would mean that we calculated GH and there was 0 kilonewtons in there. There's no force at all in GH, which could be possible. We could have had the right combination of numbers that added to 0. But since we got a combination of numbers that put this in tension, that means that the floor has to be pulling on member GH to create that tension. So I would say B is pulling down on the column. If the floor were pushing up on the column, then the column would be in compression. But since we got a tensile number, a positive number, positive doesn't mean tension. It only means tension when you draw the arrow as a tensile arrow and it comes out positive. Like if I had drawn FGH and it was upwards, showing a compressive internal force, then a positive number would be compression. That's one of the reasons that I pretty consistently draw internal forces in tension to begin with if I don't know any better. That way the positive answer does mean tension and the negative answer means compression. But you do whatever makes the most sense to you. So this would be one of the, even though it looks like there's, 1, 2, I don't even know, 10 forces on this thing, this would actually be one of the fundamental level questions, because really all you're doing is, can you draw a free body diagram and add a bunch of numbers together? That's really all you're doing in this one. So that's pretty fundamental to the whole concept of statics and mechanics. So even though it looks like this might be a tough question, it's numbered number 2. And generally, the test that I build anyway, the first numbers are the simpler problems, and the further you go, they get more difficult. And so this would be considered one of those fundamental level questions, even though it looks like there's a lot going on. Really, all you're doing is adding and subtracting numbers. All right. The other one, let's see if I can find it. The other one that I had a few, there's been a random assortment of truss questions. Nothing in particular that's consistent. This one, okay, so yeah, there's a question before I get on to this, number 6. With pulleys, is the tension in the cable the same throughout the cable always? In our course, yes. In other courses, no. If you said it with frictionless pulleys, is the tension in the cable throughout the cable always the same? Then yes, if the pulley is frictionless, and which is the case in our course, the pulleys are frictionless. The next course and the follow-on courses, the cables or the pulleys are not frictionless, and then the tension on one side of the pulley is not the same as the tension on the other side. Think about a really bad pulley. It's rusted and it doesn't turn very well, and the rope goes across it, and you pull on one side. A lot of that force doesn't get transmitted to the other side because the cable interacting with the pulley is so gummed up and rusty, and it doesn't turn very well. Versus a really smooth turn-in pulley, if you pull on one side and the other, they're pretty much the same. And so that's what we're thinking. We're thinking of these ideal pulleys that are frictionless, they're perfectly round, there's no imperfections. So it's not a 100% realistic situation, but it is the situation we're dealing with for our course. So the answer to your question is technically no, except that in this course we're frictionless pulleys and they're perfect. So yes, the tension on one side of the pulley is the same as the tension on the other side of the pulley. All right. This one, I got several questions about this number 6, so I thought I would look at it, and it is it's a good one because it's sort of a design question. This is not the level of design that would be the design problem on exam 1, but it is a design type problem. Let's get some room for it. All right. So what this one is asking, this is a kind of a typical tensile test specimen where you would, if you were testing this flat sheet of metal, or it doesn't have to be metal, whatever it is, and you want to know its tensile strength. This is the kind of specimen that you would put into a machine and pull it apart, create a stress strain diagram, and get all that data from it. So what it's asking, there's a couple of things in the text. 2024 wrought aluminum, so that's something. Considering only the normal failure, so normal when we're talking mechanics and stresses, normal means perpendicular, not like normal average, although it's still an average stress. So the normal failure in the gauge region is this thin region. We mentioned that a little bit when we were doing the stress strain diagrams, but it hadn't been a big focus. But the gauge region is the skinny part of one of these tensile test specimen. The maximum force F that can be applied before the specimen fractures. So fractures is important because that means we're looking at ultimate strength versus elastic, yielding, there's just the stretching stuff. Fracture means that it has broken in half. So we need to look at ultimate strength. It's closest to. So you do have to have some sense of like where force F is in this picture because it's not drawn. So force F is going to be a tensile force. It does, there's enough information that you should be able to figure it out because it says a tensile specimen. So tension means you're pulling on it versus a compression test of some sort. Now we got to think about in the gauge region, what would it look like if it broke? So if I chop this thing in the gauge region, fractured it there to draw my free body diagram, it's just going to be a little rectangle. I don't even know if I can draw this very well because it's so tiny, but a little bitty tiny blue, it doesn't be blue, but I colored it blue, rectangular cross section. So my equation, this is a normal stress, so sigma equals force over area. Now in this case, I want to know the force, what force causes this to happen. So I've got to go look up the sigma. And it told me that it's 2024 wrought aluminum and I want it to fracture. So let's find our material properties. Be sure, all right, so let's go back to our problem. These units that I have to work with are metric, and you have two versions of these charts. You have a US version and a metric version, SI version. So make sure you're using the right chart. Here is the wrought aluminum down here. Can I draw on this? Not really. I don't see a drawing tool, so that's fine. Right here is aluminum 2024, and it's got some other designations. T4 is not mentioned specifically in our problem statement, I don't believe. No, it's not. It just says 2024 wrought. But we're going to use the 2024 T4 wrought aluminum. Here are its ultimate strength column, and I've got tension, compression, shear. This is a normal stress, and it's a tensile test. So I want the tensile strength. So 470 looks like 470 megapascals. So that says that the ultimate strength of this material, 470 mega is 10 to the 6th pascals equals force over the cross-sectional area where I think it's going to break. And it specifically told me that assuming it broke in the gauge region, so it did tell me that, then that area is this little tiny rectangle which has a dimension of C, 24 millimeters, times a thickness of T, 11 millimeters. Now I'm mixing my metric length units because a Pascal is a Newton per meter squared, not millimeter squared. So I do have to, take that into account one way or the other. So one way I could do that is, this is going to end up millimeters squared. So I could multiply that as 1 meter is 1,000 millimeters, but it is squared, so I need to square that conversion factor. So I could do it that way. So therefore, F equals 470 million times 24 divided by 1,000. I'll do it this way: divided by 1,000 times 11 divided by 1,000. I get F is 124,080. These units would end up newtons. Looks like my answers are in kilonewtons, so 124.08 kilonewtons, which is right here, C. Again, it's always good when you land on one of the options there. Now, these problems are set up where blah, 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 before the specimen fractures is closest to. So there will always be a technically correct answer, because even if there's a mistake somehow in the problem statement, one of the numbers will be closest to the right number. Sometimes it could end up, I guess, if it's really unlucky, it ends up exactly between two numbers. If you run into a situation where you're pretty certain you're calculating everything correctly and you think there's an error in the problem, ask in the chat, since we'll be doing this in Moodle and Zoom, ask in the chat, ask on Discord, and I will check to make sure that there's not an error in the problem statement. There shouldn't be any errors, but you never know. Particularly when they're embedded in Moodle. Sometimes Moodle can generate a number that really just doesn't work for whatever reason, and it generates hundreds of different possibilities. So I can't check every one of them individually. But most of the time, you're going to get exactly one of the answers here, if it's a multiple choice. Not everything's a multiple choice on the exam, but most of them are. And so you should get one of the choices. All right. Well, those are the two that I got questions about that I thought were worth looking at, because they each have a little bit of stuff that we haven't talked a whole bunch about, particularly the pulleys. We haven't really talked about pulleys at all. I don't know that there's a pulley problem on exam 1, but just in case there is, it is good to go how you deal with them. All right. Like I said, quiz 2 is open now. I would go ahead and take it at least once. I'm pretty sure you can attempt it twice. I think I set it up that way. I would do it at least once before the exam, because it is content that will be on the exam. And then you can save the other attempt till later if you want to. You do have the outline for exam 1, and there's 3 practice sections of exams. You've got all the optional problems in Moodle, so you've got a lot of stuff you can practice with if you want to. Let's start now. Let's make a whole new page and start on this content will be for exam 2. And what we're doing now is frames and machines. Oh, can't write it in that color. Frames and machines. I kind of need to move my desk around here a little bit so I can not write at such an awkward angle. All right, that's better. Frames and machines. So sometimes frames and machines will look like trusses. Sometimes the diagrams that we draw might even look exactly like a truss, but they're not going to be a truss for one of the reasons that they're going to violate the truss assumption. So remember truss assumptions. Let's go back and talk about those really quick. or at least the highlights. So external forces were only at joints. That was a big one. Another big one would be the joints are modeled, even if they're not physically this, they are modeled as frictionless pins. Sort of along with the first thing I wrote down here is that we ignore the member weight. Or if we do consider it, we half it up and put one half of the member's weight at one end of it and the other half at the other end where the pins are, because that was, or the joints where they are. Those are the big things. These all led to every member is a two-force member. Now we did have the zero force members, so I guess they're not two force members, but same idea. So those things were true for trusses, which let us use method of joints and method of sections. A frame or a machine is going to violate at least one of these things, and it's usually this. There's usually a force on the frame or the machine that is directly applied to the member, and you can't simplify it to be at one of the joints. You can't move it around or anything. It's just applied directly to the member, and there's no way around it. And as soon as you have something like that, then that means this cannot be a truss anymore, and we cannot use method of joints and method of sections. We need to use some other system to solve for the member forces. It also means that instead of two force members, there can be two force members in a frame or a machine, but it's not guaranteed. Instead, it's guaranteed that at least one piece is going to be a beam. So for frame, and I keep saying frames and machines because they fall into the same category of how you go about solving them, but a frame is meant to be stationary and a machine is meant to have moving parts. You know, somehow it moves relative, some of its pieces move relative to other pieces of it, where a frame, it's rigid. So they're going to have the same solution procedure. Maybe it's slightly different in the order that you do things, but we'll get to that later. But they both fall into this category that they're not trusses, but they might look like trusses. All right, so frames and machines, like I said, they're going to break at least one truss assumption. And they will have at least one beam. And the beam is the part that can flex. So up until now, everything just stretched or compressed, got longer or shorter. But beams can bend and flex. So I'm using those two words interchangeably, flex and bend. And so it can do things that we couldn't do before. Not every piece of a frame and machine has to be a beam, but at least one piece does. A frame and machine might have two force members, but it's not guaranteed. They could all be beams, but it could be that one or two or a whole bunch of them, the pieces for a frame or machine, actually are two force members. And in fact, finding those two force members is sort of similar to finding a zero force member in a truss, where finding that usually makes the solution process simpler. Finding a two-force member in a frame or machine usually makes the solution process simpler. Sometimes it makes it possible. Sometimes if you don't find the two-force members, then you can't even solve the thing. There's too many unknowns. So we will look at how to find two-force members. Well, maybe we'll do that right now. Because you already kind of know, because it's basically any part of this frame that obeys all the truss assumptions probably has a two-force member. So here's how I'm going to write looking for two-force members in a frame or a machine. So again, there may not be any two-force members in a frame or machine, but there could be. So what you want to do is look for a member with exactly 2 pins. So you can't have 3 pins in like 3 bolts or whatever. You can't have multiple other than 2 pins holding this member together. If there's only 1 pin holding it on, it's just kind of dangling there and it's not really doing anything. Or it's a cable or something like that, and the other end is attached to a wall. That's different. Cables are always two-force members as far as we're concerned. And then, if you find any members that have exactly 2 pins, make sure this member does not have external forces. So again, we're not talking about internal forces like when you cut the free body diagrams and all that, but external forces. Applied to the body of the member. So, for instance, if you have a piece here, these are the 2 pins holding it into the rest of the structure. As long as I don't put a force on the body that I can't move to one of the pins, then that thing can be a two-force member. But as soon as I put some force pointing, directly to the body itself, then it's not a two-force member and it's a beam. So anything that would cause it to, flex or bend, turn it into a beam, is going to mean it's not a two-force member. Beams are not two-force members. But as long as I don't have that, I can have forces applied to the joints, and that's fine because I could do that in trusses. Then it becomes a two-force member, and it eliminates some unknowns. And so instead of having 2 reactions at every pin, you just have the 1 reaction, and it's the same on both ends. So it's very handy to find two-force members in frames and machines. All right, let's build us a very simple frame and kind of look at how we would analyze this thing, what makes it a frame, and all that kind of stuff. And then let's do one that's a little less simple, but still not terribly complicated. All right. So I'm going to have a wall. I guess I could draw it as one solid wall. I don't know why I drew it as 2 separate pieces, but I did. I'm going to have a piece here. I'm going to put a connecting piece down to here. And then I'm going to put a oddball shaped piece here just to make sure that you recognize it doesn't have to be straight. I think technically your book says that two-force members and truss members are straight members, and they mostly are. But as far as solving this thing on paper, they don't have to be straight. I'm going to put a pin here. So this will be a pin. And I'll put a roller here. And so this could still be a truss. right? It's got a pin and a roller as supports, which trusses have. It's got members that only have 2 joints at each member. One of them's crooked, but it still only has the 2 joints. This could still be a truss. But when I go and put a distributed load, or any kind of load, doesn't have to be distributed load, but I put some load like on a beam and not at the joints, then that's where it becomes a frame. So this piece is actually a beam, because if you look at it, it's got this distributed load pushing directly on the beam, and it would want to flex, you know, bend. It would want to bend or flex because of this load on it. So that turns it into a beam. Clearly not a 2-force member when it's flexing like that. 2-force members just want to stretch or compress. That's one of the reasons why they don't normally draw the crooked pieces in here for the 2-force members, because they do have a moment applied to them since they're offset, but we're ignoring that, and I just want to draw one to show if you have one, here's what you do with it. Let's put some letters, A, B, and C, and some dimensions. Doesn't really matter what these are for what we want to do. We just need some numbers. So let's see, I had some written down. Let's do 4, 7, 3, and 12 units of inches. They can all be inches. Okay, we need some magnitude for this force. Let's say that it's 10 pounds per inch. Kind of have to put it up here. It's a distributed load, so it has one of those weird units where it's how many pounds per length of distribution you have. So I've got 7 inches of distributed load, 10 pounds per inch. So this total thing, let's find some other color to put that in. I don't have a good color. Maybe this one. The total lumped load, we talked about these, I think last time, would actually be 70 pounds, and it would be set over 3.5 inches. So we just took the 10 pounds per inch spread over 70 pounds, collapsed it down to a lumped or concentrated load of 70 pounds, 70 times 10 pounds per inch. 7 inches times 10 pounds per inch is 70 pounds. And then I put it at the centroid. This is a rectangular, this would be called an evenly distributed load, where where basically the load is horizontal. The line across it is horizontal. That's evenly distributed. You could have unevenly distributed that have some random shape, or a triangle or a curve or whatever. Whatever you have, you calculate the area of the load, which is base times height, which in this case the base is 7 inches, the height is 10 pounds per inch. And then you put that load at the centroid of this shape. It's a rectangle, so the centroid would be just right in the center, the middle of it, halfway. I need to do that so that I can deal with the distributed load as a point load for equations, and then if I'm doing any sort of deflection type stuff, which we'll do later, I will redistribute it. All right, so how you deal with a frame or machine. This becomes a frame because it has a beam in it. First, you will kind of want to look for 2-force members. So any members that have exactly 2 pins, so AC and BC both have 2 pins. Neither of those have external forces that are applied to the body. They do have external forces, but they're at the pins. There's forces at A and forces at C from the pin and roller. But those are joints, so that's okay. I don't have like this 10 pound per inch load pushing on member AC or BC. So those are both 2-force members. So this is a 2-force member, and this is a 2-force member. So that will help us when we go to draw the free body diagram of things. Typically with a frame, maybe not a machine as much, but this is a frame because the way it's built, it can't really move relative to itself. None of these pieces are going to be able to change position, so it's not a machine. So when it's a frame, the typical thing you do first is find the external reactions. So let's just go over to the side and put our forces on here. And the pin at A will have AX and AY. The roller at C can only react horizontally, so we'll have a CX. And then we've got the 10 pounds per inch, which we lumped into, I'll just put it as green, 70 pounds total lumped load. I'm doing it in a different color to remind myself that it's not a separate load. Like I don't have the 10 pounds per inch distributed and a 70 pound load. The 70 pounds is the lumped concentrated version of the 10 pound distributed load. 10 pound per inch distributed load. So now I've got basically something similar to method of sections maybe. I've just got a rigid body and it has 3 unknowns, and I want to solve for those 3 unknowns. Again, it does follow the same rules where maybe you don't need to find the external reactions first. Maybe the thing you're looking for doesn't need them, but typically you will need them. And you have to solve for them before you start taking individual pieces of this and looking at individual pieces. Generally. So what I would do, I have a pin and a roller. I would do what I normally do in some moments about the pin, which I called A. I'll call clockwise positive. You have to choose one. And so I've got the 70 pounds. So this is why I wanted to do the lumped version, is so that in this equation, it shows up as just 70 pounds and it's not distributed, and I got to do some kind of calculus to account for it being spread over a distance. The calculus would end up being that you just lump it in the center, or at the centroid of the distributed load, which in this case is the center because it's an evenly distributed load. The moment arm for this thing is this distance. So that is 4 plus 3.5. I'm looking at the other picture now. 7.5 inches. So I'm going to end up with inch pounds. That makes sense for when I'm doing a moment. It's either foot pounds or Newton meters or inch pounds, something like that. It is going clockwise, so I leave a clockwise symbol on here, and that's fine. CX would go counterclockwise, so I'll give it a minus CX, and its moment arm is that 12 inches. And those are the only 2 forces that would create moments about A. Both AX and AY point directly at point A. So their line of action intersects point A, so they have no moment arm. So I could get a result here. Therefore, CX equals, it's going to be positive. Oh, these equal 0. I didn't write equals 0. It's going to be positive. So that means I drew the arrow for CX the right way. 70 times 7.5 divided by 12. 43.75 pounds. Then I could do one of my other 2 equations, equilibrium equations. Summation of forces in X equals 0. Looking at my free body diagram, I have CX plus AX equals 0. I just found a value for CX, 43.75 plus AX equals 0. Therefore, AX is negative 43.75 pounds. So what that means, that negative means I drew the arrow for AX the wrong direction. So it's not a big deal. It just means that I need to account for that either with a negative sign, or the next time I draw AX, draw it the right way. We need the other one. So summation of forces in the y direction. AY minus 70 pounds from the distributed load equals 0. So that's easy enough. Therefore, AY equals 70 pounds. It comes out positive, so I drew the AY arrow the right way. So that's typically what you do, is you find your external reactions first. So I have those. There are instances where maybe you don't have to solve all of them, or maybe you don't need to do them first. But until you recognize what those instances are, just solve for the external reactions first. Now what you do with frames and machines, and for machines, parts where the thing probably has moving parts relative to other parts in the body, this might be where you start for a machine. For a lot of times for machines, you can't solve the external reactions first. Maybe you're given the external reactions, or that's the whole point, is to figure out what they are. So if you have a machine, then maybe you can't solve the external reactions first. What you do next after this step, or you start here for a machine, is you take and you draw individual free body diagrams for the pieces of the frame. And again, I'm going to draw all of them. You usually don't need to draw all of them. There's usually just one or two that you need, but until you have a better sense of which one you need, then just draw them all. And it'll start to, the more you do it, the more you practice it, it'll start to become more apparent which ones to draw. In this case, it's probably apparent which ones to draw because there's only one that has an external force on it. And so that's probably the one you need to draw, but that's not a 100% true statement. It's just probably true. So what you do is you take your free body diagram and you unbolt it from all the pins. So A, B, and C, you remove those. Then it comes into, in this case, 3 different pieces. You draw the free body diagram of each of those pieces. So we'll start with AB. So AB is just a horizontal piece, and it has this distributed load across it, and it has a pin, and so it has a couple of things. Let's look at B first. So we decided that BC was a two-force member. So what that means is that if I connect the dots between B and C, I know the reaction for member BC is on that line. I don't know necessarily which direction it goes. It's just on that line. So at B over here, since I know that, I'm going to draw this. Let's draw it this way. So that's the force in member BC. This is 10 pounds per inch. At A is a little bit different because A is connected to member AC, but it's also connected to the pin that's holding my frame to the wall. So there's 2 separate things going on there. So for member AC, it's a two-force member. You connect the dots between A and C, which in this case line up with member AC, which is what normally happens. And so I have one force, that's the force AC, acting in this direction. So I'm going to put it just this way. Then I have to decide what to do with AX and AY. So AX and AY are the pin reactions, and they are applied to member AB and member AC. They're all connected here at this pin, connecting it to the wall. If I put reactions AX and AY on member AC, which is a two-force member, then, remember this is two-force member, so is this guy. Then it's not a two-force member anymore. If I put AX or AY or both on member AC, which is a two-force member, but I add more forces to it, then it's more than two-force member, which kind of defeats the point of it being a two-force member. So I don't want to add those AX and AY to member AC, so I need to show them on member AB. So I'm just going to put, let's draw them the right way. I did find that AX needs to go the other way. Well, let's make it more straight than that, though. There we go. 43. Now, when I do draw it the right way, I don't need that negative sign anymore. AY was correctly drawn this way. And now I've got this free body diagram. I could still, put the 70-pound distributed or the lumped version of the distributed load on here, because I'll probably need that. But it's not an additional force, it's replacing the distributed load. At this point, I could work on the problem. I could do the math now. But I'm going to go ahead and draw the member AC and BC so that we can just get through the drawing idea, and then we'll do the solution process. So really, you could stop here, do the solution process, and be done with the problem. But I want to go ahead and do the rest of the drawing first. So member AC here. Oh, I guess I could put labels on these points. So member AC is a two-force member. It has exactly 2 pins. There's no external force on the body of AC. There are those external forces at the pin and roller, but I am going to put those forces on the other pieces. So I already did draw AC here. So I do have to take into account that once I've picked a direction for AC somewhere, I have to follow that same direction through all of my pieces. So on this version of AC, this A and this A, they're the same point, so they have to have equal magnitude and opposite direction. So I need this AC to point down, and then this one is to point up so that member AC is in equilibrium. And if you don't get that part sorted out, you're going to get wrong answers all over the place, because you won't have equal and opposite reactions. So once you pick or define a direction for a member force, then you have to use the equal magnitude opposite direction on the other side of the piece. So like member AB and AC are connected to each other. Member AB has one direction and magnitude. Member AC has the same magnitude but the opposite direction for that force where they're connected at A. So I don't want to put the roller reaction CX. I don't want to put it on this piece, because it would then be a 3-force member, which means it's not a 2-force member anymore, and I have to go back to writing AX and AY. I have to do all that kind of stuff. So I want it to stay a 2-force member. So I'm not going to put the reaction at C here. So let's draw the next piece, kind of like this. B and C. And I've done the same thing where I've assigned a direction for BC when I drew member AB. So the reaction at B on member BC has to be the same magnitude, FBC, but the opposite direction. So it has to go this way. Same magnitude though. Once I assign that magnitude and direction at B, I have to have the equal and opposite one here. Whoops, not A, that's BC. Same magnitude, FBC. Opposite direction of B, because the part has to be in equilibrium. So the joint has to be in equilibrium and the part has to be in equilibrium. And so it's kind of this chain reaction of how do I get the directions correct on these arrows. Now, it could be that every one of the AC arrows is the wrong direction. Like they're all wrong. So either they're all correct, if I've done it correctly, drawing the equal and opposite reactions, or they're all the wrong direction and I get negative values for AC, which means every arrow that I drew for AC would be backwards. Same thing for BC. I drew my little dotted line in there, kind of showing that it's a 2-force member. And I still haven't taken into account member CX. So, or not member CX, but reaction CX, the reaction from the roller. And I don't want to put it on this piece either, because it's a 2-force member, and if I add a 3rd force, then it's not a 2-force member. So what do I do with it? I can't just ignore it. So what I do is you take the actual pin, the bolt or whatever is holding member AC and BC together. So there's something in this hole. You take that and put all the forces on it. So you can put CX on it. So what was CX? 43.75 pounds. I put the FBC reaction, so it's got to go this way, and AC would go down. So that way I'm still accounting for CX. It's not just thrown away, and I didn't have to put it on either member AC or BC because I wanted to maintain those as two force members. So I put them on the pin at C, the actual element that's holding member AC and BC to the roller, whatever that is. So at that point, we have drawn every possible free body diagram that we need to draw. Most of these we don't need to actually draw. Like, we don't really need to draw AC and BC. We could either just draw this pin at C or the top. Well, we couldn't draw. Yeah, we could draw the pin at C, or we could draw this member AB and get all the information we needed. Member AB. Well, remember, pin at C is just exactly like a concurrent force system with two unknowns. So we know how to do that. Let's look at this. So let's see if I can copy and put it down here somewhere. And let's work on this piece. It has two unknowns, the member force AC and the member force BC. So we should be able to solve it because it's not a concurrent force system. That means I have three equations. I can work with summation of forces in X, summation of forces in Y, and summation of moments. I can work with three different equations and only have two unknowns, so I should be fine. Let's do a moment equation. Why not? We will need some dimensions for that, though. I forgot what they were. 4, 7, and 3. So let's put them here. 4 inches, 7 inches, and 3 inches. Okay. Let's do moments about A. That should give us a value for BC. This may not be the simplest way to do it, but that's what we're going to do. I kind of want to do a moment equation with an angled force anyway, so that we are more comfortable doing that. All right, so moments at A. AC, 70 pounds and 43.75 pounds all have lines of actions that intersect point A, so they don't create moments about point A. That's the opening the door by pushing on the hinges idea, where it doesn't turn. The 70 pound, the green 70 pound, does have a moment arm. We decided that moment arm was here, which is 7.5 inches. That would be a clockwise moment about point A. I said clockwise is positive, so I'll give it a positive value here. FBC is at an angle. So we will break it into a FBCY and a FBCX. The X line of action intersects point A, so I don't have to worry about it creating a moment about point A, but the Y component has a 14-inch moment arm, so we do need to worry about that. It would go around counterclockwise, so it is a negative FBCY times 14 inches. Those have to add to 0. Now, FBCY is not what I want to solve for. I want to solve for FBC, the force in BC, not the Y component of the force in BC. So I need something with this angle. So let's see if we can get some rise over run for this angle here. The rise is 12. The run is 14. So that would give us a hypotenuse here. 12 squared plus 14 squared. Square root 18.44. and that's going to be the same, you know, as here, 12, 14, 18.44. So FBCY is actually FBC times 12 over 18.44, the y component of that. Or you could calculate the angle and do the actual cosine, sine, whichever one you want to do. So I'm going to put that value in for FBCY because it will let me solve for FBC, which is what I actually want to know. So let's see. All right, 12 divided by 18.44 times 14. So the coefficient that goes with FBC is 9.11. 70 times 7.5 divided by this 9.11 number is 57. So therefore, FBC equals, and it's going to be a positive number. When I move FBC to the other side of the equals, it becomes positive. 57.625. The units end up being pounds. So the positive number means that I drew every one of the FBC arrows I drew are the correct orientation. So that means BC, look at the arrows on B and C, they're pointing towards the body, so it's in compression. And if you look at our original picture, you could certainly imagine FBC or member BC being in compression in the way that this is sorted out. So that's what we got, is that it's in compression. All right. Now we could do summation where we have to do either another moment equation, moments about B, or, and you can do that. You know, you can do a more than one moment equation on a free body diagram, but when you do more than one moment equation, it means that either X or Y are obsolete or redundant. So it's not like you can just do an infinite number of moment equations and solve for an infinite number of variables, unknown variables. It makes other equations redundant. So what I'm going to do is, you could do moments about B and solve for AC. I'm going to do summation of forces in Y. So I've got FAC going up, so that's a positive. I've got 70 pounds going up. I've got 70 pounds going down. I've got FBC, which is going up the way I drew it. And those have to add to 0. I just found a value for FBC, so I can plug that in, and the only unknown is the force in AC. So the 70 minus 70, that goes, you know, they cancel each other out. When I plug in this 57 for FBC and move AC to the other side of the equal sign, FAC ends up a negative number, and the negative number is, let's see, 57 times 12 divided by 18.44, 37.5. And that negative sign means that every arrow FAC that I drew is the wrong direction. So looking at it, I drew it in compression, but all of those arrows are backwards from what they need to be, so it's actually in tension. So member AC is actually a tensile member. All right. That's the only unknowns. The only other equation I could write is at joint C, but those are the same exact unknowns. I guess I could write joint C to check the work, you know, make sure that these actually add to 0, but there's no other free body diagrams that I can draw that would give me any new information. All right, that is an introduction to frames and machines. I kind of want to stop there. We've got plenty of time left, but we're going to do frames and machines some more, and we kind of covered all the little pieces. I want to give that a little bit of time to sink in without going too far, because tomorrow is actually exam 1. We don't need to get too deep into frames and machines. So I kind of want to stop here and let y'all, you know, just kind of let this sit in the back burner. I'll go ahead and open up the homework for frames and machines, but it's going to be due much later. And we'll come back next week. So tomorrow we do the exam. You'll log into Moodle. There'll be a Zoom link. You can have, let's talk about what you can do on the exam a little bit. So what will happen tomorrow at noon, you log into Moodle. There'll be a Zoom link for you to log into also. So you'll be logged into Zoom and Moodle at the same time. On the Zoom, I just need a video kind of showing where you are and, you know, your test setup, sort of. It doesn't have to show your computer screen. I don't know how that would even work. Maybe if you had a separate camera to do that. But I'm kind of assuming that you're on a laptop, and it's just kind of more or less showing you. And it's sort of focused down-ish towards your work area the best you can. And you don't have to have audio on. In fact, it's probably bad if all of you had audio on and we're trying to take an exam. That would actually be really distracting. So audio's off, video's on. I'll have the chat in Zoom running. I'll have the Discord chat running too, just in case. But most of the questions I answer in Zoom. That way, I don't know, it's just simpler. We're just looking at one screen. I will have Discord running just in case, though. So you have that. You have a calculator. There's no MathCAD. You do have to write your solutions out. At the end of the exam, you're going to use your phone, unless you have a scanner. You're going to use your phone, take a picture, use one of the PDF scanning apps. There are plenty of free ones. TinyScan, I think Adobe has one. There's several that it takes a picture and it turns it into a PDF. So take a picture of every page of your work and upload those to... There'll be a upload, I don't know exactly what it's called, but on Moodle. What did I call it? Let's see if I can find it. I may not have put it up yet. Let's see, exam 1. Exam 1 work is what I called it. So you'll upload your exam 1 scans here. I use those in case you have some issue with a problem, particularly a multiple choice problem. You write down one answer, but you solved it and wrote on paper the correct thing, but clicked the wrong button in Moodle. So it's for that sort of thing. Sometimes I do award partial credit on these, but generally it's for correcting errors and making sure that you actually got the work right. If you have literally nothing written down and you have your answers, even the simple ones, write down a general idea of what you're solving, because if you have no work at all and somehow you get all the right answers, that's very suspicious looking. So just make it simple for me to say, oh no, there's the equation they wrote down. Yes, all you have to do is add these numbers and divide, but that they showed that that's what they're doing. So use it so that I can see you did a little bit of work. Some of these are going to be very simple, and yes, you could do it all in your calculator, but write down the baseline equation you're using on paper so I can know that you're using the equation. You do it after you're done, so you don't have to be on Zoom while you're scanning all this stuff in. So you can log out of Zoom when you're done with the exam, and then you can spend it. I don't leave it open very long. It's usually like 10 or 15 minutes, maybe 15 minutes after the exam time closes. I've never had problems with that, running out of time to get stuff scanned. If somehow you do have issues, then let me know and we'll fix it. But you do it after you log out of Zoom. You can sit there in Zoom if you want to. I'll probably shut down Zoom when we get to 1:50 or 2 o'clock or so. Let's see. I think that covers most of what you'll need. Most of the time, you're just sitting there, you're writing down your work. You got your regular calculator. Like I said, no MathCAD. You're going to write things in your calculator and write them on paper. It is okay. I will say this: if you have a tablet computer and you want to use OneNote, and that's where you write your work, that's fine. So you just do it all digitally, and you just send me the digital things, kind of like what I do on the Zoom here. That's fine. It doesn't have to actually be pen and paper. It can be tablet work if that works better for you. I just don't know if that works better for like your setup, how many screens you have available and all that. Also, you do have access to in the reference materials section, you have access to those, well, more than these. I have to find the reference materials. I'll put a link to the, or I'll put the exam 1 and 2 reference on this same Moodle page, so you don't have to flip back and forth. They're buried in this introduction part up here also, but I'll go ahead and put them on this page so that you don't have to look for them. You can either print those out and use them printed out, or you can use them on your screen. It's actually a little better on your screen because you can zoom in to the numbers a little easier. I think that covers the basic idea. Remember, don't get too worried. I do have it set up where the course grade, the way exam 1 and 2 work is that the one you do worse on, which is typically exam 1, is 15% of your final grade, and the other one is 25%. Plus, at the end of the quarter, you get a chance to either retake a version of exam 1 or exam 2. So you can completely mess this one up, and you still have another chance to retake not the exact same exam, not same numbers and problems, but the same content with different numbers and problems. And so you can redo that at the end of the quarter. Typically, exam 1 is the lowest average grade, but that's several things. It's the first exam. You haven't gotten used to the format. More people take exam 1 because some people do drop, and so it is on average going to be the lower of the 3. But it's actually, the content's actually not that difficult. It's just the way the numbers work out. All right, I haven't seen any other questions pop up in chat, so that's good. If you do have questions, send them to my email or the Discord channel, and we'll see if we can answer them. If I don't know if I'll get them answered in email as fast as I would in Discord. And if you send them in Discord on the general or the test, to not just directly to me, but in the channel, then everybody gets to see the answers, which is generally good, so I don't answer the same thing over and over. All right. I will see y'all on Zoom tomorrow at noon, and that we'll go from there. All right.